We have an exponential function here. We are going to go through and graph that. Could make an XY table, but if you know how to use transformations with a parent function, then you can go through and do the graphing as well as all the describing they're having us do in the directions by using the parent function and then also transformations. So that's going to be my approach here. So to start with, here is where we want to go. We take a look at the equation. I see that we do have an exponential. There is a variable up in the exponent. From there, I want to recognize what the parent function is. It's always really easy to do because you just look at the base of that exponent and your parent function equation is going to be y is equal to whatever that same base is raised to the x power. So I want to take a look and remember what the parent function looks like. Well, the parent functions, y equals a number to the x power, all of them go through the point 0, 1. They all have a y-intercept at 1. Another point that's easy to find is 1 comma and then the base. And then they also have a horizontal asymptote. And the equation for that is y equals 0, which is a horizontal line right on top of our x-axis. So if I were to draw a very quick sketch of our parent function y equals 3 to the x, y-intercept at 1, 1 comma base, which in this problem is 3, so 1 comma 3. That's another point that's on the graph. And then a horizontal asymptote right on top of our x-axis, and the equation for that is y is equal to 0. Our graph starts out on the left side very close to the asymptote, just barely above it, and then as we go to the right, it slowly gets taller, slowly increases, goes through those 2 points, and then continues to increase faster and faster as you look at this from left to right. So that's our parent function. That's what y equals 3 to the x looks like. I'm going to visualize this in my head and then take a look at this equation that we have and identify what the transformations are going to be based on what we're seeing. The addition and subtraction that's there, when you compare the two equations, there's a few things that are different. One of those is that out here on the end, we have a +1, and the other is that up in the exponent, instead of having just an x like the parent function does, the one we're trying to graph, has an x minus 2. And the addition and subtraction there, they tell us two different things. The addition or subtraction out here on the end is vertical shift. Plus is up, minus is down, so this parent function equation is going to have to be slid up 1 unit because of the +1 on the end. The x minus 2 up in the exponent, that's horizontal shift. And that goes the opposite direction we normally would think of, so subtraction actually is going to slide the graph over to the right. So if you know what the parent function looks like and you can visualize that in your head, if you take that graph, move it up 1 and right 2, then you would have the graph for this black equation, g of x. So I'm ready to graph this, and I'm not going to make an xy table to do it. I'm going to use the parent function and then the idea of transformations to do the graphing. So I'm going to take this point right here, the point 0, 1, and I'm going to move that up 1 and over to the right 2. If I do that, I would be at the point 2, 2, so that's one of the points that's on the graph. I also need to take the point 1, 3. 1, 3 would be right here. I'm going to move that up 1 and over to the right 2. That would be the point 3, 4. So taking those 2 points and sliding them up 1 and right 2, we end up with the 2 points that we're going to graph here and here. And then I also need to take that horizontal asymptote, and I'm also going to slide that up 1 and right 2. But if you take a horizontal line and you slide it left or right, it does not change the look of the line at all. The only thing that really affects a horizontal line is if you move it up or down. If you slide it left or right, it does slide left, it does slide right, but when you look at it, it's going to look exactly the same. So you could take the line and you could move it from the x-axis up 1 and then slide it over right 2. But when you do that, really all you're going to see, all that's going to be noticeable, is that your equation is going to be up 1 unit. And then from there, you can draw in the shape. Over on the left side, it starts close to the asymptote. As you go over to the right, it gently increases, gently gets taller for a little while, and then starts increasing faster and faster as you go to the right. So this is the graph for function g. I didn't do that by making a table. I took my knowledge of the parent function and transformations to take that and come up with the exact graph that we should have for that. With that said, there are a few things that we need to do in addition to graph. One of those is to list out the domain and the range and any asymptotes that we have. You can do that by looking at the graph, or slid my camera. Next time I'll slide the paper. That was weird. Anyway, you can do that by looking at the graph, or there are certain things that you're going to key in on as you do more and more of these. First of all of these exponential graphs do go forever to the left and forever to the right, so the domain on all of them is going to be all real numbers from -infinity to infinity. The parent function has a horizontal asymptote at y equals 0, but for this graph it was at y equals 1, and that's because we moved it up 1 unit. So whatever your vertical shift is, that's going to tell you where your asymptote is. All horizontal lines are y equals, and it's always going to be y equals whatever that number is out here on the end. In this case it was a +1. We had a vertical shift of 1, so y equals 1 is our asymptote. For the range, you can still use y and 1, but in between where the equal sign is, we're going to put greater than, and that's because if you take a look at our asymptote, our graph is up above it. It's all the bigger values of y. And for all the problems that we're going to be working on, our range will be a greater than symbol there. From there, we are supposed to use limits to describe the left end and the right end behavior. So for the left end, I'm going to do the limit. This graph goes forever to the left, so x is approaching -infinity when I go over to the left as far as I can, and I need to describe what the height is doing. Well, it's getting really, really close to a height of 1. And for our right end behavior, similarly, this graph does go forever to the right. As we go to the right, it does go up for forever. So we have the limit as our graph goes to the right, as x approaches infinity. Our graph goes up for forever. Our height, our y value, f of x, is equal to infinity. For increasing and decreasing, the two answers are always going to be the domain and none. And you just have to decide, does this graph increase the whole time or decrease the whole time? It's not going to do both. And as you travel from left to right, when you do increasing and decreasing, you always have to slide along the graph from left to right. As I go from left to right, it's gently increasing and getting taller, getting higher to start with, and then it increases even faster. So it's increasing the whole time. So the domain is where it's increasing the whole time, and then it is not decreasing at all. So those are the 7 different descriptions they asked us to do along with the graph.